When a high-speed neutron strikes a heavy nucleus, the resulting fission releases energy, triggering a secondary process that creates more fuel than it consumes. On April 6, 2026, the prototype fast breeder reactor at the Kalpakkam nuclear complex achieved its first self-sustaining nuclear chain reaction. India possesses just 1 to 2% of global uranium, but over 25% of the world's thorium. However, thorium is naturally fertile. It cannot sustain a chain reaction on its own, and must first be irradiated by neutrons from another fissile source. In the 1950s, physicist Homi Bhabha conceptualized a 3-stage closed fuel cycle to bridge this gap. This strategy uses the byproduct of one reactor stage to provide the fissile material needed for the next. The prototype fast breeder reactor, or PFBR, is the essential machine for stage 2. It is engineered to capture escaping fast neutrons to produce new fuel, effectively multiplying the energy potential of domestic uranium by a factor of 60. Criticality at Kalpakkam proves the engineering required for stage 2 is now functional, providing the necessary link to utilize thorium for long-term power generation. The PFBR core is powered by fuel harvested from stage 1, pressurized heavy water reactors, specifically utilizing a combination of plutonium-239 and uranium-238. The core architecture is comprised of 181 distinct fuel subassemblies, each manufactured to high-precision specifications. These assemblies contain mixed oxide, or MOX, pellets. To manage the power distribution, the core is split into enrichment zones, with 21% plutonium in the inner core and 28% in the outer core. The pellet's annular geometry features a 5.55 mm outer diameter and a hollow 1.8 mm internal diameter. This hollow center provides a pathway for fission gas release, reducing peak temperature at the fuel center and preventing structural degradation. This precise shape is a prerequisite for achieving the high power density required for fast neutron breeding without causing the fuel to melt. Surrounding this central core is a radial blanket of fertile uranium-238. During operation, fast neutrons escape the central core and strike the blanket, transmuting the fertile material into new fissile plutonium. This specific core and blanket arrangement is the physical mechanism that allows the reactor to generate more fuel than it consumes. Fast breeding requires neutrons to maintain their high velocity. Traditional water coolants are unusable here because they naturally slow neutrons down, which would halt the breeding process. Engineers instead utilize liquid sodium, which has a heat transfer coefficient approximately 100 times more effective than water. The PFBR uses a pool-type design, housing the core, primary pumps, and intermediate heat exchangers within a single main vessel filled with liquid sodium. Sodium boils at 882 degrees Celsius, allowing the reactor to operate at 547 degrees while remaining at low primary pressure. Operating at low pressure eliminates the risk of a high-pressure pipe break, which is a major safety concern in light water reactors. The trade-off is inherently chemical. Liquid sodium reacts violently if it comes into contact with air or water. To manage this, an intermediate sodium circuit separates the radioactive primary sodium from the steam generators, creating a redundant physical barrier against leaks. Constructing these specialized containment systems requires massive infrastructure, as seen here during the installation of the reactor vessel. While liquid sodium is thermodynamically ideal for fast breeding, its reactivity requires these uniquely complex and heavy engineering architectures. The reactor core is designed with a net negative power coefficient. If the temperature increases, the fuel and coolant expand, which naturally reduces reactivity and slows the chain reaction. For emergency situations, the PFBR utilizes the Safety-Grade Decay Sheet Removal System, or SGDHR. This system consists of 4 independent circuits. They are entirely passive, meaning they do not require electrical power. Hot sodium rises to air-cooled exchangers, and once cooled, the liquid sinks back down, providing indefinite core cooling. The PFBR also employs 2 independent shutdown systems, designed with different environmental triggers to prevent common mode failures. The 9 control and safety rods operate in the argon gas above the pool, while the 3 diverse safety rods are designed to function while fully submerged in liquid sodium. The complexity of these first-of-a-kind safety and coolant systems was the primary driver of a 16-year delay in the reactor's commissioning. One specific hurdle involved an obstruction in the fuel transfer machine that occurred deep under the sodium pool. Engineers resolved the issue by developing customized under-sodium ultrasonic scanners to visualize the internal mechanics without draining the reactor. Overcoming these technical setbacks demonstrated that mastering the operational engineering is as critical to the program as mastering the underlying physics. A breeder program functions as a closed loop. The full cycle is only complete when material produced in the reactor is successfully reprocessed for reuse. Stage 2 physics require an integrated industrial backend to harvest and recycle the newly bred fissile material. This is the role of the Fast Reactor Fuel Cycle Facility at Kalpakkam. It co-locates fuel fabrication and reprocessing to eliminate the risks of transporting radioactive material. Reprocessing fast reactor fuel involves handling specific isotopes like uranium-232, which complicates the recycling process. Uranium-232 decays into thallium-208, which emits high-energy gamma radiation that is dangerous to human operators. Because of this radiation threat, the reprocessing plant utilizes advanced shielding and entirely remote handling systems to manage the fuel. The facility allows the program to operate continuously, isolating hazardous isotopes while maximizing the energy extracted from the fuel. This technology comes with significant costs. The PFBR's final expenditure rose to over 8,181 crore rupees, more than double the initial estimate. These costs are justified by the need for 24/7 clean baseload power, which provides a reliable foundation for a grid otherwise dependent on intermittent solar and wind energy. To scale this capacity to 100 gigawatts by 2047, the government enacted the Shanti Act in 2025. The act introduced a tiered liability structure and removed automatic supplier liability, clearing legal obstacles that had previously deterred private and international participation. This legislative shift permits private companies to invest in and operate nuclear plants, including the deployment of small modular reactors. These reforms provide the framework for the next phase of the program, the twin unit FBR 600, which aims for a 25% reduction in capital costs. Establishing this massive infrastructure is the critical final step in securing a long-term domestic energy baseline for the entire nation. By achieving criticality, the PSBR generates the uranium-233 necessary to begin Stage 3. This process allows India to utilize its thorium reserves as a primary fuel source for domestic power generation.